So we've looked at calculating these sums of an infinite series. What we're going to do here is I'm going to present you with some questions related to this topic. I want you to read the questions, pause the video, have a crack at them, and then come back here and see how you did compared to the worked solutions. Here you go. First thing, I want you to find the sum to infinity of the series that goes 100 plus 20 plus 4 and then continues on. Second one, I'm giving you two terms, 18 and 6, and telling you they're adjacent terms of an infinite geometric progression. Telling you the sum of that, find the first term. And then the last one, what I'm asking you is what condition needs to be met before that series has a sum to infinity. So pause the video and have a crack at those. So first one, find the sum to infinity of the series that goes along the lines of 100 plus 20 plus 4, etc. Well, we know that the sum to infinity of a geometric progression is a over 1 minus r. Now that's the only one that can have a sum to infinity, a over 1 minus r. Now we know a general term of a geometric series is given by un equals a r to the n minus 1. And we know that for this limit to exist, we have to satisfy the condition where the magnitude of r is less than 1. So that's the first thing we need to check. Does it satisfy that condition? Well, my common ratio in this case is going to be 20 over 100, or it could be 4 over 20. Regardless, it's going to be a fifth. And I know that fifth, the magnitude of it, is less than 1. So there we go, we've got the condition from a common ratio. I know it's going to have a limit. It's going to have a sum to infinity for this one. All I need now is the a, and then I can plug it in. But we know that a is the first term, u1, which in this case is quite simply 100. So now that I've got all the information I need, plug it in, work it out, and I get my answer. So my sum to infinity for this one is going to equal 100 over 1 minus a fifth. So it's then going to be 100 divided by 1 minus a fifth, which is 4 fifths. Now remember, to divide by a fraction, we turn it into a times and flip it. So it's the equivalent of 100 times 5 over 4. 100 divided by 4 is 25. Times that by 5, and we get 125. So I can say fine. So my sum to infinity for that series is going to be 125. That's as high as we're going to get. Second question. Given that 18 and 6 are two adjacent terms of an infinite geometric progression, sum to infinity of that is 90, find the first term. Well, we know that a normal geometric progression, each term takes the form un equals a r to the n minus 1. So 18 and 6 are two adjacent terms. I don't know which terms along the sequence they are, but I know they're adjacent. So I can write that in a generalized format where I can say un equals ar to the n minus 1. That's going to be my 18, and the next term, which would be un plus 1, is the equivalent of ar to the n, which I know is going to equal 6. I also know my sum to infinity, which is equal to a over 1 minus r, for this one is equal to 90. So I'm able to set up this relationship here. Now I want to know the first term, which is this a here. So if I rearrange this and make a the subject of that formula, I know that a is going to equal 90 bracket 1 minus r. So to calculate a, what I first need to calculate is the r. But remember, the r is the common ratio, so it's the ratio of two consecutive terms in this case, i.e. I know that r is equal to un plus 1 over un, which I know in this case is 6 over 18, which is 1/3. Generalizing it in this format has helped me still to use my common ratio, and I can still get what that is. So now all I have to do is take this, substitute it into here, work it through, and I can find out the value of a. So I can say fine, so a is equal to 90 bracket 1 minus 1/3. So in this case it's 90 times 2/3, so it's 2/3 of 90, 1/3 is 30, 2/3 of it is 60. So I know that a is 60, so I have to now explicitly write it out that u1 is equal to 60. So my first term in that series is 60. Third question I ask you is what conditions must be met before the series 1 plus 3x plus 9x squared has a sum to infinity? Well, we know in general that the magnitude of r has to be less than 1. That has to be the case for any geometric progression for it to have a sum to infinity. However, that can be written without the magnitude sign of -1 has to be less than the value of r, has to be less than 1, has to be between these two values. It can't include it because if your common ratio is 1, nothing's going to change. Or if it's -1, all it's going to change is the signs each time. Nothing in terms of the size of the number itself is going to change, so we can't include it. The first thing I need to do is figure out my common ratio from here. Well, for my common ratio, again, look at the ratio of two consecutive terms. So I could look at 3x over 1, or I could look at 9x squared over 3x. The bottom line is I get the same thing, that my r, my common ratio, is equal to 3x. So for this series, what I can say is fine, so for it to have some sort of sum to infinity, -1 has to be less than 3x, which has to then be less than 1. Now, I want the condition to be based solely on x, not 3x, but just x itself. So if I divide this whole thing through here by 3, what I can then say is therefore if -1/3 is less than x, which is less than 1/3, I'm going to get a sum to infinity for that series. So I can pick any value between -1/3 and 1/3, plug it into there, and I'm going to get a sum to infinity. If I take a value out with that, no matter how small, I'm not going to get a sum to infinity for it. It's going to just continue to gradually get bigger and bigger and bigger, and I'm not going to get a set value. So these are just a couple of the examples of the types of question that we have to be able to answer involving sums to infinity of these series. We've got to be aware of it all, be able to work it through, and be able to understand where each of these parts come from and how we use the information that we know.